Hello, everyone. Now that we have talked about a conceptual understanding and have that through the PDF slides, we're into our first Jupyter notebook of 3 that we'll be doing with regards to inference and inferential analysis. So we're in 0504 example, and this is going to focus on simple linear regression, the same concepts we've been talking about, effect size, p-value, but we're going to discuss here how to interpret these numbers and what they mean, going through an example with some data. So this is the 0504 example notebook, and I'm going to switch to the slides view for the presentation. All right, so we have the setup cell, we've run that. And the question we're going to be asking in this notebook is, does poverty percentage affect teen birth rate? Now, I said at the beginning of any question like this is to figure out what the null hypothesis is and what the alternative hypothesis is. And you might want to think, is this the perfect question? Should it be, does poverty percentage affect teen birth rate? Or maybe a better question would be, what is the effect of poverty percentage on teen birth rate, right? The effect could be 0 or it could be non-zero, which is how we get to our null and alternative hypothesis. So our null, no effect. There's no relationship between poverty percentage and teen birth rate. In this case, beta in linear regression would be 0, right? It would be a flat line explaining the relationship between these two variables. The alternative hypothesis here is that there is a relationship between poverty percentage and teen birth rate. Throughout this analysis, we'll be able to determine in what direction, is it a positive or a negative relationship, if it is in fact something other than 0. So the alternative hypothesis says that the beta, the effect size, is something other than 0. So how do we go about determining whether we want to reject our null in favor of the alternative, or if we fail to reject the null and have no evidence to suggest that there is a relationship? So the data we'll use for this are available on my GitHub. So the URL to the text file is here. We will read it in as a text file using the sep parameter, specifying that it is tab separated. We'll store this as DF, and then once we read this in and look at the first few rows, we'll start to get a sense of the data that we'll be using here. So we can look across the columns, see we have some information about location. We have poverty percentage. We then have birth rate 15 to 17, birth rate 18 to 19, violent crime, and then overall teen birth rate. So this there in the teen birth rate, it doesn't break it down by age. And then you have these 2 columns that break it down by age. Each row appears to be a different state. So we have a few pieces of information here. And before we go determining the relationship between these 2 variables, we have to check to make sure that the assumptions of linear regression have been met. They have to demonstrate a linear relationship. They have to be multivariate normal. The predictors cannot demonstrate multicollinearity if there's more than one. In this case, the first example, there won't be, but we'll build up to this in the next notebook. The points cannot be autocorrelated, and the data are assumed to be homoscedastic. Okay, so when we start a new analysis, we start exploring the data, understanding the relationship. Here I'm using Seaborn to generate a scatter plot where the x-axis has poverty percentage, the y has teen birth rate. I'm using the DF dataset, and this just makes the points larger so it displays better. And I'm adding some more helpful x and y labels. So here is our plot with poverty percentage on the x-axis, teen birth rate on the y. We can see that each point here represents a state, and we can see the overall relationship between the points. And we can see at this point there's some sort of upward trend. This lets us know that there is some relationship between these 2 variables, but we want to measure how strong this is, right? What slope and how confident are we in these estimates? So given the increase appears linear over time, right? We see this steady, consistent increase over the values in poverty percentage. We meet our first assumption. Now, if I generate a second plot here, looking at each of these on its own, poverty percentage appears approximately normal. Now it's not perfect. And teen birth rate seems approximately normal. On your assignment, there will be code to help you formally and statistically test this, and there are tutorials to help you there. For this one, we're going to do the eyeball test. It's it's normal in both the teen birth rate and our poverty percentage, both our X and our Y. With regards to our other assumptions, they're not autocorrelated, as one value does not determine another. And there's no issue of multicollinearity because we are not looking at more than one predictor. And the data appear reasonably homoscedastic, right? We don't see a ton more variance at any one part of the distribution than another. So we've tested our assumptions, we've drawn some exploratory plots. If this were your project, you would likely have more plots, more data. We're keeping it simple for this first example. So let's get down to the math underlying linear regression. So here is the format used by statisticians to show the relationship between two linear variables. So your predictors are your x, your outcomes are your y. Beta 1 and beta 0 are representative of your slope and your y-intercept. So this is a reformulation of the y equals mx plus b that you saw in algebra. So let's first be sure we're on the same page about what our outcome is here, right? What is our y variable? Here we're asking whether poverty percentage as a predictor impacts teen birth rate. We could have formulated a different question, but as we have formulated, our predictor is poverty percentage and teen birth rate is our outcome. So outcome is our dependent variable, predictor is our independent variable. One way to go about doing this in Python is by using PATSI. There are a number of different approaches to doing statistical analysis in Python. For your projects, if you're more familiar with something else, you're welcome to use it. For your assignments, you are asked to use the packages that have been imported for you. But what we see here is that once we specify a matrix demonstrating the relationship and giving an input as our data frame, we know that poverty percentage is our predictor, as we just talked about, and teen birth rate is our outcome. This will always have the syntax y tilde x. And you can see here that we are storing this information in the variables outcome and predictors. So teen birth rate matrix is going to be an outcome, poverty percentage, and predictors. And we're using the D matrices function from PATSI. Now that we've specified those design matrices, we can run the model, and we'll use stats models for that. There are tutorials on the GitHub, on the course GitHub, if you are unsure as to what's going on here, but we've imported stats models as SM, and we're going to use ordinary least squares, OLS, to carry out our linear regression. Note here, again, we give it our outcome, comma, our predictors that we generated above for these design matrices using PATSI, and I'm going to store that in mod. Now what we have to do, now that we've generated our model using ordinary least squares, knowing that within stats models there are a whole bunch of different models that you can use and learn more about, we have to understand our results. So we store the model in mod, and now we can fit the model. So fit our linear regression to the data. We apply the fit method to our mod object, and we store that in res for results. And now we can look at the results. There is a summary method to res type objects. And what we see here are the results from our OLS regression. There's a lot of information here, and we're going to walk through a few different pieces. It is critical that you understand how to interpret this. So if you're confused at any point, I encourage you to pause it, rewind, make sure you understand what's going on. So what you see here is our dependent variable is teen birth rate. The independent variable will be down here, poverty percentage. This is our predictor. So our outcome is up here, our predictor is down here. It shows that we've done ordinary least squares as our model, and we use least squares as the method. It summarizes the number of observations here, as well as the number of degrees of freedom. We haven't talked about this. We're not going to go into detail. I'm just orienting you to all of the parts of this output. We're going to return to what's going on up here in just a little bit, but we're going to focus in on this middle part of the output, as this is really where a lot of critical information is. The first row here is intercept. The second row here is poverty percentage. So this whole row of values summarizes the relationship between poverty percentage and teen birth. The coefficient is the beta. This is the effect size determining the relationship between poverty percentage and teen birth rate. We also see that standard error is here. So you know that the value that you would most expect to see an increase, so for every 1 unit increase in poverty percentage, you would expect a 2.03 unit increase in teen birth rate, is how we're going to interpret the coefficient. And the standard error is here, letting you know how confident you are around that estimate. We're going to leave the t statistic and the for now, but we're going to return to p-value. Here, this lets you know what the p-value is. This lets you know that it is smaller than 0.000. But what we see here is that the 95-degree confidence interval for the coefficient is somewhere between 1.438 and 2.613. We haven't talked about confidence intervals, but they take into account your estimate and your standard error, saying that you would expect, given how close the points fell to the line, that this true value is somewhere, because we're uncertain of its exact value, between 1.438 and 2.613. You'll get very comfortable looking at these tables, but for now, always make sure you have the right variables as your outcome and your predictors, that you understand what a coefficient and a standard error is, that this is the p-value, and this gives you some intuition as to the range you would expect for your beta. We haven't talked about the intercept yet. This value is your y-intercept. This is your beta 0, which we'll see in just a second. So I left the clicker questions in for this example because I think they're really helpful at orienting you to making sure you understand what's going on. So the question is, what is the effect size of the relationship between poverty percentage and teen birth rate? So I'll show the values again. What is the relationship between poverty percentage and teen birth rate? The effect size. Okay, so this is something that often trips people up and why I've left the clicker questions in. A reminder, this number here demonstrates the effect size between poverty percentage and teen birth rate. This is the y-intercept. So this is the slope, beta 1. This is the y-intercept, beta 0. So the correct answer here was 2.0255. Now, I mentioned there's a lot of information in there. The 3 pieces that we've discussed previously, COEF is the beta estimate explaining the effect size in the row with the predictor. Standard error is standard error, and the p greater than the absolute value of t calculates the p-value for you. So knowing those pieces and where to get them from that output will be helpful in your understanding. Now, I started to interpret in the explanation, but let's walk slowly through this model again to make sure we really understand it. So I showed this before. Your outcome is equal to beta 0, the y-intercept, plus beta 1, the effect size, times the predictor. If we plug in the numbers from that result summary that we just saw, 15.67 is the y-intercept, 2.03 is the beta 1, the effect size, and then poverty percentage is our predictor, and teen birth rate is our outcome. If our poverty percentage were 0, so if we plugged 0 in for this number, the teen birth rate would be 15.67, right? 2.03 times 0, this term drops out. Teen birth rate would be 15.67. That's what makes this number the intercept. So your beta 0 is your y-intercept in a linear regression. The way to interpret 2.03 is that for every 1 unit increase in your predictor, so for every 1 unit increase in poverty percentage, you would expect to see a 2.03 unit increase in teen birth rate. This is measured by beta 1, your effect size, your slope. So if you went from 2% poverty to 3% poverty, a 1 unit increase, you would expect the teen birth rate to go up by 1 unit, by 2.03. Let me say that again. If poverty percentage increased from 2 to 3, you would expect teen birth rate to increase by 2.03 as determined by the beta 1. Okay, so beta 0, y-intercept, 2.03 here is your beta 1. That is your effect size, your slope. Tells you how much you would expect teen birth rate to increase given a 1 unit increase in your predictor. Let's look at these results again. Here, which value represents the expected teen birth rate if the poverty percentage were 0? So which of these numbers is what you would expect the outcome to be, teen birth rate, if poverty percentage were 0? All right, so you should be clued into the fact that if poverty percentage is 0, 0 times this beta 1 will be 0, and you would expect the teen birth rate to be 15.67, right? It's going to be that y-intercept. It's going to be your beta 0. Now, what does this look like visually? Here, I'm creating a scatter plot. I'm also plotting the data and a line showing you so that I can explicitly include this model. So this should look very familiar. Beta 0 plus beta 1 times our x's will give us our y's. So if I generate this scatter plot and then add this dotted line, which is our model, to it, this is the first time we're really seeing what linear regression looks like after mathematically defining it, right? So I have specified what line to draw, given the data underlying it. And we can see that it does a pretty good job describing the relationship between poverty percentage and teen birth rate with these data. So this is what we saw on previous videos. The model, the line mathematically describes the relationship, but it doesn't explain it perfectly. This is, again, the concept between the fact that all models are wrong. And now the question is, if I told you the poverty percentage of a state was 15, what would you estimate would be its teen birth rate? So if the poverty percentage were 15. So for those of you figuring it out, the way you determine this is you go to your plot here, and then you go up to the model and say, okay, what would the outcome be here? Maybe it's about 45, right? That's doing the eyeball estimate. You can also plug this in to your equation and calculate exactly what your estimate would be. Now, you can't tell me that it will certainly be teen birth rate, right? There's some uncertainty around this line, but you can tell me what your best estimate would be. Pulling up those results again. You could plug 15 into poverty percentage, multiply it by 2.03 and add 15.67 and get the exact estimate for teen birth rate. So you'll have to do this on an assignment. If you wanted to answer what is a reasonable estimate or guess for a state with a poverty percentage of 20, you would put 20 in here, multiply it by 2.03, add 15.67, and then take a look at the outcomes here. And you can see that there are some pretty close values. All three of these are reasonable estimates for a state with a poverty percentage of 20. And this is because, again, there is uncertainty in our guesstimates and our estimates. There is standard error. We can't say for sure what the outcome will be. We can give it our best estimate with some level of certainty. So if I told you a location's poverty percentage, what would you guess its teen birth rate would be? The way to do this quickly is doing 15.7 plus 2.03 plus 18. So if it were 18, birth rate would be 52.21. If it were 12, birth rate would be 40. You know, you always want to make sure these calculations make sense. 12 is less than 18, and our beta is positive. So you would expect this number to be larger than this number, and it is, right? Like you always want to make sure that the numbers you're getting make sense given the data, given your understanding of the model. So we've just gone through an analysis. We started with the question and our null and alternative hypotheses. We carried out linear regression. And my question is to you, how would you conclude from this analysis? So our question is, does poverty percentage affect teen birth rate? Or what is the effect? I'll edit it here. On teen birth rate. So you have to first decide whether or not you are going to reject or fail to reject the null. And then what that interpretation is. Is it there's no relationship between poverty percentage and teen birth rate, or there is a relationship between poverty percentage and teen birth rate? So this is somewhere where students struggle. So feel free to pause and think a little longer. But first, we just saw that there is a relationship, a linear relationship. We looked at the beta and saw that there's an increase by 2 units every time poverty percentage increases by 1 unit. We saw that the p-value was quite small. Now, there is no magic p-value. P being less than 0.05 doesn't mean that it's meaningful, but taking the plot and the model and the beta and the standard error and the p-value all together suggests that there is a relationship between poverty percentage and teen birth rate. So now we're between B and D. And our null said that there was no relationship. So we are going to reject the null in favor of the argument that there is a relationship between poverty percentage and teen birth rate. So B is the right answer here. All right, I encourage you to look over this, play with the examples, make sure you understand each step here before we start talking about confounding and multiple regression.